right, hi everybody. So let's keep on doing a few more examples on how to use substitution for indefinite. And then once we do a few of these, we'll be able to rock and roll for definite integrals after this. So let's do this example. So let's say we have the integral from, let's say we have the integral of dx over the square root of 4 minus 7x. Now here, of course, we're going to use substitution, not only because we are in the section of substitution, but because right here we see that we have an inner function. And as I mentioned earlier, when you have the best and easiest way to find your u is to see if that u is usually contained in, parentheses, square root, or in another function of that sort. Now, I wrote it this way, but we don't actually have to write it this way, but I just wanted to write it this way just so that you can see that we can also write the integral, this dx on top. This is the same thing as writing as the integral of 1 over the square root of 4 minus 7x dx. Okay, so as mentioned like half a second ago, I'm going to let this inside piece be our u. So as always, I'm going to do my u is equal to 4 minus 7x. Now we have to take the derivative of u with respect to x and write it as a differential. So the derivative of this is going to be negative 7 dx. But nowhere in our function over here do I see a negative 7. So I can't replace it. I have something to replace this x function here, and this dx u. But in order to do that, we have to rewrite this to be negative 1 over 7 du equals dx. So now we have something to replace dx and then this x function here. And so now we can rewrite this as the integral from 1 over root u du. And don't forget about that negative 1 over 7 that we like to write in the front. Okay. And now we can just integrate this. But before we do, I would recommend that we rewrite this in terms of powers because that's the way you're used to integrating. So 1 over the square root of u is the same thing as u to the negative 1/2 du. Okay. And now after that, we just apply that power rule for integration, and we'll get that negative 1 over 7 times, and since we are integrating now, we can get rid of the integral sign, that fancy little s, and then this is going to be 2u to the 1/2, because if we add 1 to this, we're going to get positive 1/2, and remember we have to divide by that new exponent, which is, if you divide, it'll just get the reciprocal. And then we can't forget about our plus c over here because guess what? It's a indefinite integral and not a definite integral. So indefinite integrals need this plus c. Okay, so now what we're going to do now is we can write, distribute that negative 1 over 7 so that we could get negative 2 over 7 u to the 1/2 plus c. And now, of course, we're going to replace u by our original function, which was up here, which is u is equal to 4 minus 7x. This is equal to negative 2 over 7 times the square root of 4 minus 7x plus c. And that's basically it for this example. That's our answer. And so now let's do a few more. I think I only have 1, 2, 3, 4 examples left for this. And that should get you all set up for Calc 2, for our final exam, and for your homework. So it's going to be great. Okay, so let's do another example. Okay, so what I want to do is I'm going to integrate 1 over 3x plus 1 dx. Now, how do I integrate this? I don't think I can, right? Like we can't rewrite this to be in the power rule. And even if we did, right? Don't write this down, but even if we did rewrite it as a power rule, we would have the integral of 3x plus 1 to the negative 1 dx. And now we see we do have an inside function. We have a 3x plus 1, but the issue here is this negative 1. Remember that we can't do the power rule if we have a negative 1. I mentioned this earlier in the earlier sections that power rule, when we add 1 to the x1 and divide by it, only works for anything that's just not negative 1. We actually have a different rule for when that happens. And the reason this doesn't work, if you've come to my office hours, I explained this, is that if, let's say, we were to try to apply it, let's say we try to apply it, then if we did try to apply it, then this would be, this is wrong, by the way, but it would be 3x plus 1, negative 1 plus 1. Well, and then we would divide by negative 1 plus 1. Well, that's just 0, so this would be 0, so this would just be 3x plus 1 to the 0 power over 0, which this up here is 1 to the 0 power. Well, this is undefined, so that integration technique doesn't work for this. So that means we have to look at a different. Sometimes we have to use different methods, right? And so recall that whenever we had something that was to the negative 1 power, that was an ln function. So now let's recall. Hopefully you remember this, but recall that if we have the integral of 1 over x dx, right, the answer to this is the natural log of x, the absolute value of x plus c. So that's exactly what we're going to use to try to solve this one here. So now to solve that top one, we're going to, let me rewrite this. We're going to let u equal that bottom function, because I'm going to, that's like a inner function as well. And so that du is going to equal 3 dx. Don't forget the dx. And now, like I said, we have something for our u. This is going to get replaced by u, but we need to fully get this replaced. So remember, we need to match the puzzle pieces together. And here we have this 3 tacked on. So it's going to be 1 over 3 du is equal to dx. And now we're ready to rock and roll and replace it in there. So let's go ahead and replace it in there. This is going to be 1 over 3, 1 over u du. And now we could easily see that the integral of 1 over u du is definitely and indeed natural log of u. So we'll replace it by that. So this is going to be 1 over 3. And then now, like I said earlier, the integral of 1 over u du is going to be the natural log, the absolute value of u plus c, because we're dealing with a indefinite integral. And now we can replace u by the original function 3x plus 1. Let's go ahead and do that. So I'm going to distribute the 3 while I'm at it. So you're going to get ln, absolute value of 3x plus 1 plus c. And that's our answer. Okay, a few more, just introducing different functions, because we can apply u substitution. Of course, we can apply it to square root functions. We can apply it to large powers. But it's also applicable for different types of functions, and we've seen different types of functions before as well. We've done it with a sine. We've dealt with sine functions, e functions, and I actually don't have an example for e, but I'll probably throw one in at the end of the section. So let's do a little bit of a more complicated example, and actually, let's move on to a new page so that we have a nice and fresh page. So for example, zoom in a little bit. Okay, let's say we had this crazy integral. We have x plus 1 times the square root, ooh, it's about to get crazy, x squared plus 2x plus 5. Look at this crazy integral. It's a lot going on. Dx. Okay, so previously when I introduced the u substitution, let's go back to the definition for a second. Over here. Okay, the definition says if u is equal to g of x, is a differentiable function whose range is an interval I, f is continuous on I, then this is how we are going to substitute. Notice that g of x was our inner function, and the thing right next to it was the derivative. Coincidence? No. That's because it works. That way we're able to substitute it in, and then we can replace it all by u. So because that does work, that's how we're going to apply u substitution, is we're going to choose u so that we can substitute for something whose derivative is also in that function. So what do I mean by that? So you're going to pick u so that when we take that derivative, the derivative is also there. And so u is typically the most complicated thing. It doesn't always work, and for this class it will, but when you move on to Calc 2, you're going to learn other methods of integration. This isn't the only method of integration. And you actually want to make sure you have this locked down and ready to go for Calc 2. And I would actually strongly recommend that a week or two before you start Calc 2, you come back and you review u substitution, because on that first day, they're going to start with u substitution, I promise you. Okay, so we're going to let u equal x squared plus 2x plus 5. So this is what I'm going to let u equal. And the reason I'm going to let u equal that is because when I take the derivative of this, I'm going to get 2x plus 2 dx. Sorry. Got a little ahead of myself there. And now we're going to get, I'm going to go ahead and substitute that 2 out, because I noticed that I have something to replace this piece here. I have a dx, but I also need to replace x plus 1. And I'm not quite there yet. I have a 2x plus 2, and I have to put that in my original function. So I need to do a little bit of manipulation here in order to get that to work. But don't worry, it's going to work, I promise. So then we're going to factor out a 2, and then we're going to get x plus 1 dx. And look, here we have an x plus 1, and here we have an x plus 1. Perfect, almost ready to go. Now we got to get rid of this 2 here because we don't have any 2 in our integral originally. So we're going to have 1 over 2 du is equal to x plus 1 dx. Excellent. And now see, we have a x plus 1 dx, x plus 1 dx, and our u is going to get replaced right here. So perfect. Everything we need to go. So we're going to get the integral. And then that 1/2, I like to put it in the front of the integral, so we don't have to deal with it, because remember, it's just a constant. We're always allowed to pull those out. Very nice. And so now we're going to do the square root of u du. Beautiful. And everything else, so all this x plus 1 lives in the du. Look at, we let the 1/2 du equal 1 plus x. So it's fine. Everything's good. Always check that everything you have is getting substituted in correctly, and that you're not missing any of those puzzle pieces. And now you know how to integrate this. It's super easy. You don't have to, but if you want to rewrite it as 1/2 du, go ahead if it makes it easier for you. And so when we integrate this, we're going to get 1/2. Integrate this, we're going to get 2 over 3, because we are adding 1 to that exponent, u to the 3/2 power plus c. And now we're almost done, but we have to come back to what u originally was and plug it in right over here. This is going to be 1/2 times this times 2 over 3 x squared plus 2x plus 5 3/2 power plus c. And I guess that I should have distributed this in earlier, right? we would have distributed it in. I don't know what's wrong with my talking today. I would, these twos will cancel out. So this is the same thing as having 1 over 3 times all that. Okay, so we can do it a little bit more complicated, but just make sure that whatever you pick as u, that your derivative is also in that function. So always check that. All right, let's do a trig function, and then we're gonna do a really juicy trig function. Okay, but before we do the really complicated juicy trig function, I'm gonna do a regular one so that you can see how trig functions work. We have all different types of functions. They're all fun and cool. Okay. So if we have the integral of sine 3x plus 1, right, we know from previously that the antiderivative or the integral of sine is definitely negative cosine. But that only was true for when we had just x or just a single variable in there. And I mentioned before that, you know, what if there's something else in there? What do we do? And the answer to that is we just do u substitution. We're going to let u equal this nice inside function. Like I said, it's going to be trapped in some parentheses, some type of craziness. And then so we're going to let u equal 3x plus 1. Du is going to equal 3 dx. Yep. And now we are going to replace this by u. We have a dx. We got to get rid of the 3. And hopefully by now you're used to this. So it's going to be 1 over 3 du equal to dx. And now I could go ahead and substitute that in. This is going to be 1 over 3 sine of u du. And we know the antiderivative sine of u du. We definitely do. It's going to be 1 over 3 times negative cosine of u plus c, and u is equal to 3x plus 1, so we're going to go ahead and substitute that in. This is going to be negative 3 cosine. I'm distributing in that 1 over 3 now. And cosine of 3x plus 1, subbing it back in, and then plus c. Beautiful. Okay, and now for maybe our second to last example, because I think I want to do an e function, just so you can see how that works. All right, let's do the really nice, fun trig function one. Let's say we have the integral of sine 5x to the 7th power times cosine of 5x dx. Okay. Here's a problem. I said, let u be thing in the parentheses, but what if you have a lot of inside functions? I have an inside function here. I have an inside function here, and then I have this inside function because I have a 7th power. What do I do? Okay, I said it's typically the thing inside the parentheses, and it is. But let's say you have multiple things inside multiple functions, kind of like here. What do you let u equal? Usually it's the most complicated one that's trapped in various composite functions. So right here, for example, this is going to be sine here is trapped into this big, bigger function. So that's what I'm going to let u equal. I'm going to let u equal sine of 5x. But that's not the only reason that I let u equal that, because that wouldn't have worked if this cosine was not here. And the reason for that is because if I take the derivative of u, which is sine of 5x, I get cosine. And so remember I said you want to pick u so that when you take the derivative of it, it's also there, which it is. That's what I want. So that's what I'm going to let u equal. That's why I said it's not always a thing in the parentheses. It usually is, but you have to make sure, like, I want to say like 90% of the time it is. But you want to make sure that when you take the derivative of whatever you let u equal, it's all here. Okay, it has to be in here or it will not work. Okay, so let's continue. I'm going to let u equal sine of 5x. So this is going to be our u inside here. And now when I take the derivative of this, I'm going to get cosine of 5x. And be careful here because don't forget that the derivative of sine is positive cosine, but the integral of sine is negative cosine. So just be careful with that. And so now I have a dx here, but don't forget we have a chain rule here, so we're going to have a 5 on the outside. And so we can rewrite this as 1/5 du equals cosine of 5x dx. And look at that. I have this whole thing is getting replaced right over here by 1/5 du. Perfect. That's exactly what I wanted. So that's going to be 1/5 times the integral, and now I'm going to have u to the 7th power du. Whoa. Whoa. We just got a huge complicated function, and now all we have to do is integrate u to the 7th power. That's it? Yeah, that's all you have to do, because guess what? All your u's, all your du's are containing these craziness functions over here. And that's why u substitution is amazing, because there's no way we can integrate this without it. Okay? At least not now in this class. Okay. So now integrate this. You've been doing this. So now you're going to go 1/5 u to the 8th power divided by 8 plus c. And now we're going to plug back in what u was equal to. So this is going to be sine of 5x. I'm going to write it like this, to the 8th power over 40. That's an 8, I promise you. Doesn't look like it. Plus c. And that's it. You make something super complicated that's hard to integrate to something simple. Super simple. Okay? Now, I was done with all these examples, but let's do a really quick one so you see how an e function works. Okay. So let's say we have the integral of e to the, I don't know, 9x. It doesn't really matter. I just want to show you how this would work. But I think you have a feeling of how this would work. So we know that the integral and the derivative of e to the x is just e to the x. But here, like I said, I mentioned this at the beginning, is that we didn't have any constants in front of here. But now we do. So whenever you have an e function, it's going to be equal to this top part here, unless it's super overly complicated. But then, so you're going to like, let me actually erase this craziness. I made it look all crazy. So u is equal to 9x here. And then our du is going to equal 9 dx. Time for me to go to sleep. Okay. And so we have something to replace the 9x by a u. The e function is not our, the e is not, the exponential part is not our issue. The issue is the 9x there. We need to replace it. So now we need to get rid of this 9, so we're going to write 1/9 du is equal to dx, so that we're able to replace dx by this part over here. So let's rewrite this. So we're going to get 1/9 times the integral of e to the u du. And now the integral of e to the u is just e to the u, so this is going to be 1/9 e to the u plus c. And so now we replace it. It's going to be 1/9 e to the 9x plus c. And that's it. Usually, typically, this happens instead of, remember, when you have the derivative, you this one up here always ended up being up here. Now it's basically like you're going to divide it. That happens very often. Unless this is like an x squared term, then we have to do something a little bit different there. But yeah, that's pretty much it. Practice, 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 practice doing this. And then on the next video for the next part of this, we're gonna do definite integrals on this. And it's basically same procedure, so make sure you lock this down first. Same procedure, but for definite integrals, we're definitely going to need to account for our constants of integration. So we'll see that in the next video.